Section 310 is derivatives of inverse trigonometric functions. First example is going to relate an inverse trigonometric function's derivative to the trigonometric function that's associated with it. And so that you should see how these are interrelated, and then we'll just memorize what the derivatives of these inverse functions are. So the first thing I want to remind you of is that y equals sine inverse of x is the same as saying sine of y equals x. Those two are equivalent statements. It's by definition what an inverse trigonometric function is. I want to remind you too that while I will use this -1 inverse notation, some instructors may use arc. So instead of saying sine inverse, they may say arc sine. They mean the same thing. And the reason I point this out is because the final is departmental, and the instructor who wrote the problem about trigonometric inverses may have used arc instead of the -1 notation for inverse. So just be mindful of that. But more importantly, this statement is equivalent to this one, and that's good because I know how to find the derivative of sine of y equals x. I can use implicit differentiation. So we know the derivative of sine is cosine. Then we come back and take the derivative inside. The derivative of y is 1, but I just took the derivative of a y, so I'll put dy dx. The derivative of x is 1. I want to get dy dx by itself, so I will divide both sides by cosine of y. And that could be rewritten as secant of y, if we wanted to write it as secant of y. But way back from trig, whenever you took that either in high school or in college, right, the trigonometric functions were always related to a triangle. And what we know is that this original function here, this sine of y equals x, we know that x we could think of it as, right, being x over 1. The angle is actually y, so that little angle right there is y. And you should remember from right triangle geometry that sine is opposite the angle over the hypotenuse of the triangle. So what we know is that x should be what's opposite of our y angle here. So x is the leg that is opposite our y angle, and our hypotenuse is 1. And we don't really know what this guy down here is, this leg here. We'll call him z. We're not sure what he is, but we can find him out because we know that leg squared plus leg squared equals hypotenuse squared for a right triangle. So if I want to find out what z is, I would get, let's see, 1 squared is 1 minus x squared, right? I'd get z by itself, apply the square root, and so I now know that this z is the square root of 1 minus x squared. Now you may say, how the heck does that help me, and why are we doing this? We'll go back down to our derivative here, where we have 1 over cosine of y, or secant of y. I'm going to look at the cosine of y. We could do it with secant if we wanted to, but I'm going to look at 1 over cosine of y. I'm going to rewrite the 1. Cosine of y, I can go get that from my triangle up here. If sine of y is opposite over hypotenuse, cosine of y is adjacent over hypotenuse. And if I look at my triangle, what is adjacent is my z over the hypotenuse, which is 1. But hey, z is actually the square root of 1 minus x squared. So cosine of y is the square root of 1 minus x squared. Now we got to be a little careful here. We know we can't ever divide by 0, right? So we can't let x squared become 1, because we would get 1 minus 1, which is 0. So when is x squared equal to 1? Well, at positive or negative 1. And then you can question it, put it on a number line or whatever, but what you're going to find is that the only way you can plug any numbers into this is if the x's are between negative 1 and 1, but not equal to negative 1 or 1. If I were to plug in a 3, I would get 1 minus 3 squared, which is 9. 1 minus 9 is a negative 8, and we can't take the square root of negative numbers. So that's why I can only plug in numbers between negative 1 and 1. You could put this on a number line and test some values, and you'll find that only these work. So we're stating here 1 divided by square root of 1 minus x squared, provided that x is between negative 1 and 1. All right, well that actually is the derivative of sine inverse, and here are all the derivatives of your inverse trigonometric functions. I'm going to point out that you really only have to memorize 3. Memorize sine, memorize tangent, memorize secant, the inverse, the derivative of their inverses, because cosine inverse is just you negate sine inverse. Cotangent inverse is you negate tangent inverse. Cosecant is you negate secant inverse. And notice these are all the cofunctions, and just like in your regular derivative functions, all your cofunctions, when you take their derivative, give you negative answers. In fact, a lot of books, whenever they see minus 1 over square root of 1 minus x squared, they don't call that cosine inverse, they just say it's a negative sine inverse. So it's completely dependent on you, but what you want to do, but you need to memorize at least these 3. Now, you may hate this idea. Most people get tangent inverse because it's pretty easy. It's got a t in it. A t looks like a plus sign. It's the only thing that has a plus. I don't know. People like it, okay? They like tangent inverse. Pretty easy to memorize. Where students start getting messing up is they don't memorize sine inverse and secant inverse correctly. So I can tell you what I did when I was in school. You may hate it, but the sine inverse of x, the I kind of looks like a 1, there's a minus, there's an x. That helped me memorize that it was 1 minus x squared, as opposed to the secant, which was x squared minus 1. I don't know if you like that or not, but it helped. I knew that there was an x squared and a 1. I just couldn't remember which came first. So, and it was easy to remember that secant was icky because of the absolute value. So I knew I knew this went with the secant. That wasn't a problem. I just could never remember which guy went first, so that helped me. If that helps you, great. If not, okay. Memorize it however. Just get it memorized. All right. So let's evaluate f prime of square root of 3 if f of x is tangent inverse of x. All right, well, we know that f prime of x is 1 over 1 plus the argument squared, and our argument is x. So now when we evaluate it at the square root of 3, we would have 1 over 1 plus the square root of 3 squared. So 1/4. All right, let's find the equation of the line tangent to the graph of g of x equals secant inverse of x at this particular point. Equation of the line tangent tells me I have to use the point slope formula, and it's going to require a point, got it, and a slope. I don't have that, but I can get it. All right, remember the way we find the slope for a tangent line is we find the derivative and evaluate it at the point. So g prime of x is inverse secant, right? The derivative of inverse secant. So we would get 1 over absolute value of x square root of the argument squared minus 1, and my argument here is an x. So tangent, or slope tangent, right, is 1 over absolute value of the square root of 2 times the square root of the square root of 2 squared minus 1. The square root of 2 returns a positive value, so the absolute values here are not needed. Square root and a square, inverses of each other, right? So we're just going to get 2 minus 1. 2 minus 1 is 1. Square root of 1 is 1. So we end up with 1 over the square root of 2. Because we're going to go put it into a formula for the equation of a line, let's rationalize this so that we don't have a square root in the denominator. So there's our slope, square root of 2 over 2. And we'll now say y minus our y value equals our slope times x minus our x value. We'll distribute there. Square root of 4 is 2, 2 divided by 2 is 1, and we'll add pi divided by 4 to both sides, and leave it. You really can't do anything to make that look better, so just leave it like that. All right, if you have an argument that is not just x, or just a single variable, if it's got other junk in with it, right, then you need to consider the chain rule. So just jumping in, here's what it would look like. The 3 tags along. Oh, and it's not dx, it is d theta. Our variable here is theta, so we're going to take the derivative with respect to theta. All right, 3 tags along. Cosine inverse is a -1 over the square root of 1 minus our argument squared. But because our argument is not just a plain old x or a plain old theta, it's an 8 theta, we need to come back and take the derivative of the inside. So here's what's happening. The 3 tags along because it's a constant. that's being multiplied. We want to take the derivative of the outer piece, so that's here, and multiply it by the derivative of the inside, so that's here. Clean this up. So you'd get a negative 24 divided by the square root of 1 minus 64 theta squared. And you're done. And on this next one, I want to point out a few things, simplify it just a little bit before we attempt to do the problem. So first of all, it's z, not y, and it's w's, not x's, so we've got to be mindful of that. Here we have 8 times sine inverse of w minus 1 divided by pi times cosecant inverse of w plus 1/9 e raised to the w. Just want to remind you that those are equivalent statements, and I like to pull constants that are being multiplied or fractions that are being multiplied. I like to pull them off to the front. Helps me visualize what I'm supposed to do. All right, when I name my derivative, now a lot of students get lazy and they start writing stuff down and they're just sloppy, right? Not acceptable. You are probably planning to be an engineer or at least in some STEM field, and you have to be precise. If you're not precise, bad things happen. Bad things. Like the space shuttle delivers something to the space station, and it's in inches rather than centimeters. So, bad things happen if you're not precise. We have to be careful. Okay, so when I'm looking at this, the name of this function is z. So when I go to write my derivative, it's going to be dz divided by, or not divided by, dz over dw. We're going to take the derivative of the function z with respect to the variable w. So dz, always, it's the name of the function and the variable of the function. That's how you determine what your derivative's name should be. So dz, dw, you don't say divided by, yikes. Okay, so anyway, 8 is going to tag along. Sine inverse is 1 divided by the square root of 1 minus the argument squared, and our argument here is w. The 1 over pi will tag along. Cosecant is a negative 1 over absolute value of w square root argument squared minus 1. The 1/9 tags along. The derivative of e to the w is e to the w. You come back and multiply by the derivative of the exponent and ln of the base, but those are both 1s, so I'm not even going to write them down. And then clean this up. So dz dw is 8 divided by the square root 1 minus w squared. A negative times a negative is positive. 1 over pi. We don't know if w is positive or negative, so he must remain inside of an absolute value. W squared minus 1. And then here we would have e to the w divided by 9. All right, here we've got a nasty chain rule going on. So it's cotangent inverse of 3x to the 4th plus 5x raised to the 1/2 power. So for the chain rule to work, we have to take the derivative of the outer piece, leaving the inside alone. Then we come back and take the derivative of the inside piece. The problem is the inside piece has two parts to it as well. So we would take the derivative of its outer portion, leaving the inside alone, and then come back and take the derivative of its inner portion. So there are actually three derivatives that are going on here, and notice we're working from the outside in. Layer 1, layer 2, layer 3. All right, so this is what it would look like. We would have dy, because the name of the function is y and the variable is x, so dy dx. Cotangent, it's a co-function, so we know it's going to be negative, and the derivative of tangent inverse is 1 over 1 plus the argument squared, so the derivative of cotangent inverse would be a negative 1 over 1 plus the argument squared. So to be 1 plus the argument squared, and the argument is this guy right here, square root of 3x to the 4th plus 5x. So notice I took the derivative of the outer piece and left this inside piece alone. It's still sitting inside and looks exactly like it did in the start of the problem. All right, so I have taken his derivative. Now I want to move to this piece, and I notice it's a chain rule as well. The 1/2 will jump out front, leaving the inside alone, and I will subtract 1 from the exponent. So I have to leave this inside alone, so it's going to stay 3x to the 4th plus 5x. So I've taken the derivative of that sort of middle piece, or the middle layer. Now I want to come back and take the derivative of the inside, which should be 12x cubed plus 5. And then we just clean this up. So lots of things that can happen here. We'd have a negative times 12x cubed plus 5 all over this 2, 1 plus, excuse me, square root and a square are inverses of each other, so they'll go away. And then this guy is going to get dragged across the fraction bar because it's a negative exponent, so he's going to be brought across the fraction bar. When he comes across, he'll become positive, but we know that a 1/2 power is equivalent to saying the square root. So I would probably rewrite this just because I'm hyper about it. I like to put my square roots first if I can, or at least in this problem I do. And then we'll rewrite it so that our terms are in descending order. Pardon me. Okay, so moving on from there, sometimes it's convenient to work directly with the inverse, and we've given you some tiny examples here. It becomes it can become really helpful, but this is kind of, I don't know, kind of wordy, and it's a little bit difficult for students to understand. So I suggest that you maybe think of this as a, you recognize this as a formula, and that your book is trying to relate some things here. So if f is differentiable, so we're going to let f be differentiable and have an inverse on some interval. Okay, we're not really concerned about the interval right now. We're just saying, hey, f has a derivative and it's invertible, right? Then let x sub 0 be a point inside your interval at which the derivative evaluated at that point is not 0. Usually when they tell you, hey, it's not 0, that's because they're probably going to divide by it, and they don't want you dividing by 0, right? So there's usually some forewarning there that there's going to be division, and sure enough, that's what we see. Then F inverse is also differentiable at the point y sub 0 equals f of x sub 0, right? Y naught equals f of x naught. And we have this statement. So to understand this theorem, let's just think of some point on the graph of f, and that's sort of what they're telling you here, right? So x naught, y naught lies on the graph of f. Well, if functions are inverses of each other, then the domain, or the x values, of one become the range, or in other words, the y values of the other. So if x naught, y naught lies on the graph of f, then, wow, that is not written very well. Then y naught, x naught lies on the graph of f inverse. And so what we end up, or what we could prove if we needed to, is that the slope of the line tangent to the graph of f inverse, so the slope of the line tangent to this graph, is the reciprocal of the slope of the line tangent to that graph at their respective points. And the theorem that we're talking about here, right, says we can actually evaluate the derivative of the inverse function without finding the inverse function itself. That's where it becomes important, because sometimes the inverse function is crazy hard to find. I don't know if you remember doing this, but in one of your algebra classes, you might have been asked to find the inverse, and so you would have to switch your x and y values and solve for the new y. And that can just be terrible sometimes. So anyway, here's an example of that. So if a function is one-to-one, then that means we know it has an inverse. It's invertible. And often in the past, we would just go find this inverse. Well, that's going to be super hard, because right now, what we've got is y equals square root of x plus x squared plus 1. And if we switch our x's and y's and try to solve for the new y, it's going to be difficult because we have two different types of y's here. So this is where this theorem comes in handy. We don't actually have to go find the inverse to know something about it. All right, so right now, we need to find the slope of the curve f inverse at the point 3, 1. So this point 3, 1 is for the inverse, meaning that when it relates to the original function, this would have been the y value and this would have been the x value. So in other words, the point 1, 3 lies on f, while the point 3, 1 lies on f inverse. And if you ever question that, if you get confused by it, just take these numbers and plug them in. If for some reason you get confused and you think that 3, 1 lies on f of x, you could plug in the 3 and see if it gives you 1 as an answer. And man, this is going to give us 10 plus the square root and yikes, no, that's no good. What about the other way? What if it's 1, 3? So if you get confused by the wording, because the wording can be confusing on these, you can always just check to see, but sure enough, yeah, that does give us the 3. So when you plug a 1 in, you get 3 for your original function. So 1, 3 is for the original function f, which would mean that 3, 1 lies on the inverse. Okay, so here's how we would use the formula, right? The formula says, and I'll try to put it here as well. So the formula says f inverse's derivative at y sub naught is equal to 1 over f's derivative at x sub naught. So if you want to know something about the inverse's derivative, you would just find the reciprocal of the original function's derivative. They're evaluated at different numbers, but we'll come back to that. So how do we deal with this for this problem? Well, the first thing I'm going to do is rewrite it. So f of x is equivalent to x to the 1/2 plus x squared plus 1. All right, I'm just doing a rewrite here. Here is my original function f, and I need to know its inverse, or dang it, its derivative. So I am going to find the derivative here. So the 1/2 jumps out front, subtract 1 from it. The 2 jumps out front, subtract 1 from it. The derivative of 1 is 0. I'll rewrite this. It's 1 over 2 square root of x plus 2x. All right, it's not enough to know what f prime is. We have to know what f prime of x naught is. So what x value should I be plugging into my original function? I should be plugging a 1 in. So f prime of 1 equals five halves, right? Because that's 1/2 plus 4 halves, so 5 halves. So I don't have to go find my inverse to actually be able to answer this question, right? The slope of the curve, slope is just derivative. So if the curve is f inverse, then what they're telling me to find is f inverse's derivative at a particular y value. So what number am I plugging in for y? Well, that would be 3. So f inverse prime at 3 is equal to 1 divided by f prime at 1, which we have just found to be 5 halves, and so that reduces to 2/5. So what's clunky is, I think the notation makes this clunky. So just remember, if you can figure out what is allowed or what you plug into the original function, then this is your x and this is your y value. So we could figure out f inverse prime at the y value if we knew what f prime was at the x value. So that's why we went and found f prime, plugged the x value in, and then just plugged it into our formula.